Aim. Have you ever wondered how a forecaster knows when the weather is going to change? Follow this direction to make a barometer and do some forecasting of your own.
Requirements: scissors, balloon, large glass jar, large rubber band, plastic straw, glue, 3 by 5 inch card, marker, tape. Procedure: cut a piece from the balloon that is large enough to stretch over the top of the jar. Secure it in place with the rubber band. Put a drop of glue in the center of the stretched balloon. Set one end of the straw on top of the glue so that it is lined horizontally. Place the jar on a flat surface near a wall. Holding the card lengthwise, write low at the bottom and high at the top of it. Tape the card onto the wall next to the jar. Check the weather report, including air pressure, for your area every day for 2 weeks. Check your barometer each day. Monitor the barometer closely before, during, and after any storms. Record your results. Conclusion:
When air pressure is high, the air will push down on the balloon in your barometer, causing the straw to point to high. When air pressure is low, the straw will point to low. High air pressure generally indicates clear weather ahead, while low air pressure indicates cloudy weather. Changes in air pressure usually mean the weather will be changing. A barometer is very helpful when making predictions about the weather. Aim. Kids, do you know Sir Isaac Newton?
No.
He was a great scientist who introduced the 3 laws of motion. 300 years ago, Sir Isaac Newton figured out how and why things move. Let's study the first law of motion. Kids, I will demonstrate this experiment.
requirements:
3 by 5 inch index card, small drinking glass, nickel.
procedure:
Place the index card over the top of the glass. Place the nickel in the middle of the card so that it is centered over the top of the glass. Then flick your index finger against the edge of the card. The card will move forward and the coin will drop into the glass.
Conclusion: This is a demonstration of Newton's first law of motion regarding inertia. The card and coin are at rest and stay that way until acted on by a force. Your finger provides the force to move the card, but it does not act on coin, so the coin stays behind. It falls into the glass because the card is no longer there to support it.
Aim. Newton's third law of motion states that every action has an equal and opposite reaction.
Requirements: 11 feet of plastic fishing line, plastic drinking straw, oblong-shaped balloon, paper clip and tape. Procedure: Slip one end of the fishing line through the drinking straw. Find a place where you can stretch the fishing line at least 10 feet and tie each end to something secure. Attach both ends of the line, making sure that the line is taut. Blow up the balloon and secure the end with the paper clip. Tape the balloon rocket to the straw as shown. Position the balloon at the beginning of the line. Remove the paper clip to release the rocket. Conclusion:
Newton's third law of motion states that every action has an equal and opposite reaction. When you remove the paper clip, the air escapes from the balloon in one direction. This action produces a reaction. The balloon moves forward in the opposite direction. Aim. Kids, have you seen things floating on water?
Yes. No.
Lighter things float and heavier sink in water.
Requirements: 3 pieces of lightweight string, pencil, 2 large metal nuts, desk lamp or other object to hang string from, 2 small drinking glasses, and water. Procedure: tie one end of the first piece of string to one end of the pencil. Tie one end of the second piece of string to the other end of the pencil. Tie one metal nut to the dangling end of each piece of string. Tie one end of the third piece of string around the middle of the pencil. Tie the other end to a desk lamp or other subject so that the pencil hangs over a flat surface. The nuts should be suspended about an inch above the surface. Arrange the glasses on the surface so that one nut hangs inside each glass. You can adjust the pencil to make the nuts even with each other. Fill one glass with water. The pencil will tilt. Conclusion:
In the air, the metal nuts are level because they weigh the same. In other words, the downward force of gravity is actually equal on each nut. When you add water to one glass, the nut inside is acted on by an upward force called buoyancy, which in effect makes the nut lighter. The pencil tilts down on the side that has more weight. Aim. Sometimes it's hard to tell whether or not an egg is hard-boiled. Bobby, can you tell which one is hard-boiled? We can find it out using inertia. Let's see how.
Requirements:
Hard-boiled egg. Raw egg.
Procedure:
Place both eggs on a hard, flat surface. Spin the hard-boiled egg with your hand. Place your finger on it for just a second to stop it from spinning. Now spin the raw egg. Place your finger on it for just a second to stop it from spinning. Do you notice any difference between the two eggs?
Conclusion: In this experiment, the force of your finger on the hard-boiled egg is enough to stop it from spinning. The hard-boiled egg is solid, so the force acts on the egg as a whole. Although you exert roughly the same amount of force on the raw egg, it still spins slightly after you touch it. That is because the force acts on the hard shell, but not directly on the liquid inside the raw egg. The liquid continues to move slowly for another minute or two due to inertia.
Aim. Every magnet has an invisible field around it. It is called a magnetic field. Let us perform an experiment to see what the magnetic field looks like.
Requirements: old scissors, little steel wool pad, 2 bar magnets with north and south poles marked, sheet of plain paper. Procedure: Carefully cut the steel wool into tiny pieces. Place one magnet on a table and hold the paper about ½ inch above it. With your free hand, sprinkle the steel wool bits on top of the paper. Shake the paper a little, then hold it still. A paper will start to form. Move the paper away from the magnet and shake it again. Does the pattern disappear? Now place the two magnets side by side with an inch of space between them. Set up the magnets as opposites of each other, so there is north and south pole at each end. Hold the paper with the steel wool pieces over the magnets. How does the pattern look this time? Turn one magnet around so that both north poles are at the same end. Then hold the paper over both magnets again. Conclusion:
The steel wool bits on the paper are attracted to the line of force or the magnetic field around the magnet. The pattern you see is the shape of the magnetic field. When you change the position of the magnets, the pattern of the magnetic field changes too. Aim. Let's study some more properties of magnet.
Requirements:
Wooden ruler, plastic bottle cap, paper clips, coins, aluminium cookie sheet, nails, magnet, sheet of paper, handkerchief, drinking glass.
Procedure:
Spread out the ruler, bottle cap, paper clips, coins, cookie sheet, nails. Try to pick up each of the materials with the magnet one at a time. Make a pile of the things that are attracted to the magnet. Now try to block the magnetic attraction. Put a sheet of paper between the magnet and an object. Does it block the magnetic effect? Next, see if the handkerchief can block the attraction. Can the drinking glass interfere with the magnetic attraction?
Conclusion: A magnetic field is the area around a magnet in which the magnetic force can be felt. Magnets attract objects made of iron or steel. That is why the magnet was attracted to the nails and paper clips. The magnetic field is strong enough to penetrate some materials, but not others. As you can see, the magnet works through paper and cloth, but with glass, its effect weakens.
Aim.
Magnetic attraction can create some remarkable attraction. Look at this one. It will amaze you. Requirements:
Drinking glass, long bar magnet, piece of thread, paper clip, tape.
Procedure:
Set the glass upside down on a table. Place the bar magnet across the top of it so that it extends at least an inch over the edge of the glass. 2. Tie one end of the thread to the paper clip. Touch the other end of the paper clip lightly to the bottom of the magnet so that the paper clip hangs from it. Pull down on the thread very gently so that the paper clip is still attracted to the magnet, but there is space between them. It may take a few attempts to get this right. Without changing the position of the paper clip, tape the thread to table. The paper clip will appear to defy gravity.
Conclusion: The magnetic force acts on the paper clip to pull it up. You exert another force on the paper clip by pulling the string down. When the two forces are equal, the paper clip appears to float in the air.
Aim. Some objects are naturally magnetic, but magnets can be created too.
Requirements: steel sewing needle, bar magnet, clean plastic margarine container, water, dishwashing liquid, thin slice of cork, and a tape. Procedure: rub the needle across the bar magnet at least 30 times in one direction. Fill the container with water and place a drop of dishwashing liquid in the center. Put the cork on top of the dishwashing liquid. Then place the needle in the middle of cork. When the cork stops, the ends of the needle will point north and south. Spin the cork gently with your finger. When the cork stops, the ends of the needle will point north and south. Conclusion:
Non-magnetic iron or steel is made up of tiny units that have their own north and south poles. The units are jumbled up, so the poles face in different directions. If something causes the units to line up with all the poles facing in the same direction, the iron or steel becomes magnetized. When you rub the needle with the bar magnet in this experiment, you line up all the poles in the steel. The needle becomes magnetized and points north. So kids, are you having fun?
Yes.
Aim. This next experiment is positively electrifying. It is related to static electricity. You will learn how to create static electricity by manipulating a property called charge.
Requirements: 2 balloons, 2 pieces of string, each 1 foot long, wool sweater or scarf. Procedure: blow up both the balloons and tie off each end with a knot. Attach 1 piece of string to each balloon. Hold the balloon by the strings and touch them together. What happened? Now rub the balloons on the sweater or scarf. Hold the balloons by the string and touch them together again. What happens this time? Conclusion:
Atoms are made up of very tiny particles. Some of these particles, protons and electrons, have a property called charge. Protons have a positive charge and electrons have a negative charge. Charges that are the same push each other away, and charges that are different attract each other. All atoms have equal numbers of particles, so the charges cancel each other out. When you first touch the balloons together, their atoms have equal numbers of protons and electrons, so they cancel each other out. The balloons are neutral to each other. By rubbing the balloons on the sweater or scarf, you knock electrons off the atoms in the wool. The electrons stick to the atoms in the balloons, causing them to become negatively charged. Since both balloons are negatively charged, they repel or push each other away. Aim.
Let's perform an experiment to see static electricity at work. Requirements: large plastic bag, lightweight tin baking sheet, small metal object such as a key, wood table, baseball sized piece of clay. Procedure: place the plastic bag, baking sheet and metal object on a wood table top. Press the clay into the center of the sheet so that it sticks to it. Grasp the clay and rub the bottom of the sheet back and forth on top of the plastic bag for a minute or 2. Do not touch any part of the sheet while you are doing this. Turn off all the lights in the room to make it easier to see the spark. Using the clay as a handle, pick up the sheet and hold it near the metal object on the table. A small spark should jump from the sheet to the metal object. Conclusion:
Static electricity is the buildup of charge on the surface of an object. By rubbing the plastic bag, you cause static electricity to build up on the baking sheet. The wooden table and the clay do not attract static electricity, but the key does. Because the key and the tray have unlike charges, the static electricity on the tray jumps to the key. You see this transfer as a spark. Aim. Kids, have you ever held a cup of hot cocoa on a cold day and felt your hands getting warmer?
Yes.
That feeling is a result of heat conduction.
Requirements: butter, which is slightly softened, 3 spoons, roughly the same size. Out of that, 1 is metal, 1 is wood, and 1 plastic. 3 small beads, a cup filled with hot water. Procedure: place a pea-sized dab of butter at the end of each spoon handle. Push a bead into each dab of butter. Place the spoons into the cup of hot water with the handles pointing up. Make sure that the handles do not touch each other. Which bead falls first? Conclusion:
When something is heated, its molecules begin to move faster. Moving molecules bump into each other molecules, making them move too. This process called conduction is one way heat energy spreads. Some materials are better conductors than others. For instance, metal is a good conductor. When you do this experiment, the heat from the water tends to move more quickly up the metal spoon, warming the butter and causing that bead to fall first. Aim.
Kids, I want to ask you a very interesting question. Can I help you to keep warm? Requirements:
2 pieces of aluminium foil, 2 outdoor thermometers, paper towels, water, 2 saucers, freezer.
Procedure:
Fold the aluminium foil to make 2 loose pockets. Leave an opening at one end of each pocket so the thermometers can slip in and out. Put a thermometer in each pocket. Soak one of the paper towels in water, then wrap it around one foil pocket. Wrap a dry paper towel around the outside of the other pocket. Lay one pocket on each saucer. Place both in the freezer. Check the temperature of each thermometer every 5 minutes for 20 minutes. Does one stay warmer?
Conclusion: as water begins to freeze, it gives off energy in the form of heat. When the wet paper towel begins to freeze, it warms the air around the thermometer just a little, so the temperature is slightly higher than that on the other thermometer. Once the water on the paper towel has frozen, the air begins to cool again.
Aim. Do you ride bicycles?
Yes.
Can anyone tell me how do the brakes on the bicycles work?
Requirements: 2 dry blocks of wood, approximately 1 by 2 by 3 inches, dry bar of soap. Procedure: hold 1 block of wood in each hand. Rub the blocks together for about a minute. Stop rubbing and feel the surfaces that you rub together. Press the dry bar of soap on each block. You may have to press hard to coat the surfaces with soap. Rub the blocks together again. Does it feel different this time? Conclusion:
Most surfaces are slightly rough and will not slide past another surface easily. Friction is the term for this resistance. It takes energy to overcome friction and make materials slide past each other. A lot of that energy is converted to heat. You can feel that heat after you rub the blocks of dry wood together. When you add soap, the surfaces do not get as warm. Soap is a lubricant which makes the surface slippery and allows the object to slide past each other more easily. Aim. You may not be able to see air around you, but like all other matter, it takes space and has weight. Let's prove it.
Requirements: 3 pieces of string, each 12 inches long, ruler, wire hanger, 2 large balloons, sharp pin or needle. Procedure: tie one end of a piece of string to the center of the ruler at the 6-inch mark. Tie the other end to a hanger so the ruler hangs horizontally below it. Find a place to put the hanger, such as on the clothing rod inside a closet. Blow up both balloons to the same size. Attach the remaining strings to the balloons as shown. Tie one balloon to the ruler at the 1-inch mark and tie the other at the 11-inch mark. Adjust the strings to make the ruler level and the balloons balanced. Burst one balloon with the pin or needle. Conclusion:
Matter is any physical thing that takes up space and has weight. The air around us is made up of matter. When you blow up the balloons, you show that air takes up space. You also show that air has weight with this experiment. When you hang the 2 air-filled balloons from the ruler, it's balanced because they weigh the same. When you burst one balloon, the air escapes. The popped balloon does not weigh as much as the unpopped balloon. The weight of the air in the unpopped balloon pulls that side of the ruler down.
Did you all enjoy learning super simple experiments?
Yes, Maya. Maya, Vayu, we are very thankful to you for teaching us these experiments, as we carry them in our day-to-day life but were not aware of them.
Don't worry, kids, we are here to help you. Any one of you has any more queries?
No, Maya. No, Vayu. Bye, Maya. Bye, Vayu. Bye.
So, kids, enjoy your party and hope to meet you soon.
Bye.
Big is the world in which we live. It has so much to give and so much to give. There is so much to know while we grow. Lots of things